This chapter is all about the role that water vapor plays in weather. Water vapor, when it condenses, releases energy in the form of calories, and that is the fuel that energizes cloud buildup, thunderstorms, hurricanes, tornadoes, etc. So it's important to understand how this happens. This is a link to a video that shows fantastic cloud formation. Keep in mind that the energy locked up in water vapor is being released, causing clouds to get higher and higher. Look over these learning objectives. After you've completed watching the slideshow, go back and review them to ensure your understanding of each concept. Water vapor. In case you didn't know it by now, water vapor is the most important gas for weather processes. It's a heat-absorbing gas and the source of all condensation and precipitation. It rains water. Snow is water ice crystals. Unlike Venus, where precipitation is sulfuric acid, Earth is incredibly lucky. This is the water molecule. It looks like Mickey Mouse, with the head being the oxygen and the ears the hydrogen atoms. The arrangement of the atoms in the bonds gives the molecule a slightly positive side and a slightly negative side, giving the water polarity. This is what makes the water molecule behave in the kind of miraculous way that it does. With all these amazing properties of water listed, it also has special heating property. So that polar bond makes water wet. Water is an excellent solvent. It gives water surface tension, causes capillarity, without which plants wouldn't be able to live if it wasn't raining. The fact that water has capillarity, that polar bond, that's the positive and negative charges pulling each other up by the plant roots, causing those positive negative atoms to be pulled up into the plant itself, so it can get water even if the soil isn't wet. So the change of state of water. Water can change phase from solid to liquid to gas at Earth's prevailing temperatures and pressures. These changes of phase require the absorption or the release of heat energy, and that energy is measured in calories. The definition of a calorie is the amount of heat energy required to raise the temperature of 1 gram of water 1 degree Celsius. Water vapor has hidden heat that we call latent heat. This means that it can contain extra calories of energy without a corresponding temperature change. That's why it's called hidden. We can't see that the extra energy has produced a change in temperature. For example, 1 gram of liquid water can be at a temperature of 100 degrees Celsius. And if it absorbs 100 calories, it will vaporize, but still the temperature will be 100 degrees. Where did the energy go? It went into breaking the bonds, not changing the temperature. So this slide shows the different changes of state of water. All of these terms you're familiar with in your normal everyday life, so don't lose your common sense when you think about these in terms of weather. Evaporation is the process of converting a liquid to a gas, and it takes 600 calories of energy to convert 1 gram of water to vapor. We call that the latent heat of vaporization. Those calories of energy have to be absorbed by the liquid water in order for it to vaporize. Condensation is where we have a gas changing back to a liquid. Those 600 calories that were absorbed now have to be released. We call that the latent heat of condensation. Melting is when a solid changes to a liquid, and it requires the absorption of 80 calories per gram of water. That's the latent heat of melting. Freezing is the reverse process. Liquid goes to solid, and those 80 calories are released. So I know it sounds counterintuitive, but freezing is actually a warming process for the air, because when water freezes, the energy that was locked into that water is released into the atmosphere, which causes it to warm. Other phase changes include sublimation. Sublimation is the conversion of a solid directly to a gas without passing through the liquid state. Ice cubes do this. Dry ice, which is really solid carbon dioxide, does this. At the prevailing temperatures and pressures on Earth, carbon dioxide can only exist as a gas and as a solid. It can't exist as a liquid. Deposition is when vapor converts directly to a solid. So water vapor goes directly to a solid without passing through the liquid state. We call that white frost or hoarfrost. Let's do this one. So you see we have water as a solid, water as a liquid, and water as a gas. So as we go from a solid to a liquid to a gas, heat has to be absorbed. So if you remember what the definition of a calorie is, the amount of heat energy that it takes to raise the temperature of 1 gram of water 1 degree Celsius. So if we're going from a solid at 0 degrees to a liquid at 0 degrees, then that ice has to absorb 80 calories of energy to melt. So where did that energy go? This is what you have to think about, and this is where we go back to what the definition of temperature is. Temperature is the measurement of the speed of movement of molecules. So in a solid, those molecules are not moving very fast at all. So when those molecules of water stick together, they're moving so slow that they don't come apart very easily. So we have ice. If that 1 gram of ice absorbs energy, 80 calories of energy, then those molecules begin to move a little bit faster. So that energy, those calories go into breaking those bonds, not into raising the temperature of the liquid, which would still be at 0 degrees Celsius. Now, if we're at 0 degrees Celsius and we need to get to 100 degrees Celsius to vaporize the water, then that liquid, if we're taking it 1 degree at a time, then that liquid has to absorb 100 calories of energy. So we got 80 to get from the solid to the liquid. Then from 0 to 100 in the liquid, we have 100 more calories. And then to get that vaporized, we have to have 600 calories of energy. So all in all, that's 600 plus 100 plus 80. So 1 gram of water, 1 gram of ice would have to absorb 780 calories of energy to become a vapor. And conversely, if it goes back the other way, those calories are going to be released into the atmosphere. So when heat is absorbed, that heat energy is coming from the air. So even though the water is warming up, the air is cooling down. And if you ever forget that, just remember that when you sweat, evaporation takes place. Well, what happens to your body temperature? It cools down. Evaporation is a cooling process. Condensation and freezing, those are warming processes for the air, because that energy locked into those molecules, locked into the water, is going to be released into the atmosphere. So going from a solid to liquid to a gas, yep, the water warms up, but the air cools down. Going from a gas to liquid to solid, the water cools, but the air warms up because that energy is released into the air. So this shows some fog. Fog is condensation. Fog is where water vapor has cooled down enough so that that vapor is condensing, so it's losing energy. Dew. Think about when we mainly see dew. It's in the early morning. Well, what happened to temperature overnight? The temperature cooled down. Clouds, same thing. The temperature is cooling. When warm air rises, it cools, and if there's enough water vapor in that air, it will be cooled, it will condense, so we get a cloud. All these things are considered to be condensation of water vapor. So this is dew, photoshopped, but still lovely dewdrops. So when do we see this? Early morning. Temperature cools off overnight. Remember what the recipe for a cloud is. You have to have water vapor, you have to have condensation nuclei, and you have to have cooling temperatures. Well, overnight we get cooling temperatures, and if there's enough water vapor in the air, it condenses, and then everything's coated with liquid water. Patio furniture, spider webs, every sprig of grass, the hood of your car, the windshield of your car, everything. This, on the other hand, is deposition. This is where vapor went directly to a solid without passing through the liquid state. So you get this feathery looking icy deposits on windows, outside of windows, on your car windshield, and that looks totally different than dew. Dew hit the liquid point. The dew point was above freezing, so it was liquid. This is where the dew point actually is below freezing, so that water vapor goes directly to a solid. And this, again, lovely picture of frozen dew, photoshopped probably, but still you see that those are little ice pellets. So what happened was overnight the temperature dropped to the dew point. The dew point was above freezing temperature, so we have dew. Then the temperature kept dropping overnight, reached the freezing point, and those dewdrops froze. That looks totally different from, well, I can't go back, but the picture before with the frost. So now that we know the importance of water vapor, we need to know how to measure water vapor in the atmosphere. So there are measurements of humidity. There's several different measurements of humidity, and we'll talk about a few of them, but for our purposes, we're only going to use one of them. But water vapor is a gas. Just like any other gas, we can measure the pressure that it exerts. So if we're doing that, we say, okay, what's the vapor pressure of water? The amount of pressure exerted by the water molecules. So you just have to remember that the water vapor capacity of air is temperature dependent. Warm air can hold more water vapor than cold air can. That's why when the air is warm and we have a high relative humidity or high water vapor content, it feels muggy, you sweat, you can't evaporate, so you just stay wet. So that's one way to do it. But as the temperature changes, as the temperature goes up or down, the vapor pressure is going to go up or down, all because the vapor capacity of air is temperature dependent. Mixing ratio is the most accurate way to measure water vapor content in the air, because we're actually measuring the mass of the water vapor in a parcel of air. So it's the most precise, but it's also the most time-consuming one to do. So we usually don't even hear about this. This is not the one used by meteorologists. The one that we use most of the time is relative humidity. Most familiar, but most misunderstood because of how it changes. You might be listening to the weather in the morning and you see the relative humidity is high. You listen to the weather report at noon, the relative humidity is low. You start listening to the weather report in the evening and the relative humidity is high again, and you're thinking, whoa, what happened during the day? There wasn't really any change in the weather that we had, But something did change during the day, and that something that changed was the temperature. So the relative humidity will change as temperature changes, and the reason for that is because of the formula that we use to calculate relative humidity. Relative humidity is equal to the content, how much water vapor is in the air, divided by the capacity, how much could the air hold at a particular temperature. And that is temperature dependent. Remember, vapor pressure, temperature dependent. So as the temperature goes up, then relative humidity is going to go down because that capacity goes up. As the temperature goes down, relative humidity then goes up because that capacity changes. So there are two ways that relative humidity can be changed. If moisture gets added or removed, and that kind of makes sense. That one is not hard to understand. But if the temperature changes, as temperature goes up, relative humidity decreases. As temperature goes down, relative humidity increases.